All right, let's kick this off with a demonstration. Come on back. Okay. What I have here is a galvanometer. This measures small amounts of current. What does this measure? Small amounts of current. Okay. I'm going to hook this up to a solenoid. Okay, it's just a wire, single wire that's wrapped several times. We'll just say around a toilet paper roll. Okay. Okay. Do I have any type of power supply here? No. Okay. Just a single wire. I have a bar magnet. Okay. Let's say it was like 200 years ago, and for whatever random reason, I had this setup going on. Okay. And I was playing around with the magnet, like, choo choo, choo 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 choo. Whoa. I mean, it's kind of a random setup, but like, what? Whoa, crazy. What? Like, and if I was entrepreneurial and had like this eureka moment, how could I sell this idea and be a quadrillionaire at this moment in time? What did I just like? What idea could I sell? What? Sorry, I can't hear your thoughts. I know it's in there. What did I just what could you sell this as? Like, oh my goodness, look at this. I could do if I upscaled this, because this measures what? Current. Like, if I made this bigger, what could I do? I know some of you know this. Making electricity. We're making, like, dude, you just produced, I could light a light bulb if I upscaled this. Does that make sense? Like, we just made electricity with wire and a magnet. Like, what? Crazy. Okay? We just made a generator, a small example of a generator. Okay? So, so in that first example, I was moving the magnet across the wire. But I could also take the wire and move it through. Focus. It's just a circuit project. You all have one, hopefully. Okay. You're making small amounts of current. Okay. This is not me shaking it. If I'm holding it up here, I'm not shaking, like it doesn't move. Of course it doesn't move. It's not hooked up. Not moving. but you go through here. See that, the glare, it's a horrible glare. Moving back and forth. Good with that? Okay. Have a seat.
Built a cardboard box over top of it. I mean, put in 2 minutes.
Okay, by the end of this lesson, you'll be able to describe how voltage and current is created with a conductor and a magnetic field, describe how a generator works, and describe the difference between AC and DC. Okay, foundational fact number 3. If the conductor is experiencing a changing magnetic field, then voltage is induced or created across the conductor, and if the conductor is wired in a complete circuit, then current is created. Okay? There is a right-hand rule associated with this, but I'm going to let you learn that in college, or whenever the next time you take physics. Okay? But experiences a changing magnetic field. So, we have a magnetic field. So let's pretend we have a horseshoe magnet, a really big one. So we got North Pole, South Pole. And I'm going to put the South Pole behind the board. So we have North Pole here, creating a magnetic field going into the page. Okay. I've got a conductor, let's say copper. Is copper magnetic? Is copper attracted to magnets? No. Okay, so nothing's happening here. But the copper is filled with charged particles, electrons and protons. If I were to take this if I were to take this copper and run it through, pull it through, all of a sudden these charged particles are now moving through a magnetic field. Okay? What happens when charged particles move through a magnetic field? Charged particles will experience a force. Good job. And which charged particles are able to move? Your thoughts are so loud. Somehow it's not connecting to your voice. Which ones are able to move? Yes, I hear it. Good job. Electrons. Okay. Show me which way the electrons, if we're moving them to the right, which way electrons are going to be forced. Which way electrons are going to be forced as we move them to the right through a magnetic field going into the page. Electrons are going to be forced down, back of the hand. Okay? Yes? Leaving protons marooned behind. If you were an electron, would you like this scenario? Would you like this arrangement? You're like, yeah, it's cool. We're just hanging out with other electrons. That's exactly what no, it's like horrible. Where would they rather be? Here. Protons. Why can't, so do you see how there's a motivation to go somewhere else? that would constitute an electric potential difference. That would constitute a voltage. There, we just induced or created voltage as we pulled this across. We have not yet created current because they can't go anywhere. They're just like, boom, just packed down at the bottom. They're like, ah. How we doing? Yes? No? Okay. But if we gave them an alternative path that happened to go through a light bulb, would they take it? Yeah, they're like, woo, we're out of here. And just happens like, thank you. And then when they hit here, what happens if this conductor is still moving? Electrons still, yes? So now we have an induced current. We've created a current because, so experience the change in magnetic field voltage is induced across the conductor. That's the segregation, the polarization of the charges. And if conductor is hooked to a complete circuit, then current is created. Okay? So if electrons are flowing this way, by definition, what's the direction of current? Going in the opposite direction of electron flow. Thank you very much, Ben Franklin. It's really not his fault. He just had a 50-50 shot on hypothesis. It's just the rest of us. We're like, yeah, let's just carry it on. So current's going the opposite way, bless you, the opposite direction of electron flow. Out of positive into negative, but through the conductor goes from negative to positive to make a complete loop. Good with that? Okay. So current has been created. Simple model of a generator. Good? Okay. Here we're looking down on top of this. So this is the right-hand wing. This is the left-hand wing. Show me. Okay. Electrons are being forced up. So this becomes positively charged. B. Good with that? Is there a current created at this point? Just an induced voltage. Next question. Trick question. Correct answer is C. Why? There's no complete circuit. There's a complete circuit for it. So voltage is induced Negative side, positive side, no current. That's how you give it away. Tell your neighbor.
It also says as the conductor moves out.
Okay, correct answer is. So this is, sorry, I should have specified. This is the conductor that which way I want current. I'm asking which way current's going through. So it's going up. Electrons are being forced this way. So electrons are going this way. Current goes in the opposite way. Goes out of positive into negative to the left. B. You okay with that? Here's a quick hack. This is embracing Ben Franklin's convention. When you have your hand like this, Ben thought positive things flowed. So if you just consider positive things flowing, that's going to be in the direction the current's going. It's kind of embracing the lie, but that's what everybody's been doing. Like that's how the right hand's set up. Good with that? Okay. So, I'm running this conductor. And this is my conductor. I know it's not a conductor, but we'll say this is a conductor. I'm running it through here. At some point, I'm like, oh, shoot, I ran out of magnetic field. Light bulb goes off. Build a bigger magnetic field, yeah. At some point, it's going to run out, right? Shoot, what could I do? Maybe if I ran it back the other way, if this was hooked up to a circuit, would current be produced? Yeah. But what would the difference be? What would the consequence of that, of running it back through be? Current's going in the other direction. Does that make sense? Would that still light a light bulb? Yeah. Like, oh, sweet. So I could like go back and forth, back and forth, back and forth, back and forth. It would work. Okay? And we actually, to match today's standards, I need to go back and forth 60 times a second. That's really rough mechanically. Does that make sense? Like jackhammer, like, okay? Oh man, things break down when you do that. But check this out. The hack has been if we spin it in a circle. You see how the shadow of this goes back and forth? It's hard to do the projector, but does everybody see how the shadow is going back and forth as you spin it in a circle? It essentially does the same thing as doing this. And we can spin something 60 times a second real easily, and it doesn't break down. And so that's what we did. We took a wire and we're spinning it 60 times a second in a magnetic field, and it produces current. But the current it produces is different because the current is shifting directions. And so we have what's known as alternating current. Okay? So alternating current, AC, current that flows back and forth 60 times a second. And this is the current. This is produced by generators. Good with that? DC, or direct current, DC, this is current that flows in one direction. Out of positive into negative. This is produced by batteries and solar panels. Anything like chemically for producing electricity chemically wise, it's going to be direct current. Anything we're doing mechanically wise is going to be alternating. Okay? AC, DC, that's where the band got its name. That's why the lightning bolt. Okay? Good? Questions there? Question for you. Electricity in our outlets. Is that AC or DC? Where do we get our electricity from? Like, where does this come from in here? Comes from outside the lines. Where do those get their electricity? The power companies. Do the power companies, electric companies, do they have big batteries or big generators, you think? Big generators. So all this stuff coming out of here, the outlet, are AC, alternating current. Okay? I've led you to believe that all current so far is DC. Comes out of positive into negative. Okay? That's the only electricity produced by batteries. Okay? This is one of the reasons why we have the green power supply. Okay? It takes our AC and converts it to DC, and it brings it down to a safer level. You're not going to die. Okay? The yellow knobs on the green power supply, that's alternating current. Good with that? Okay? If you've ever been shocked before, that vibrating feeling, that's because of alternating current. Okay with that? Okay? So, here would be a simple model of a generator. We have a magnet, creates a magnetic field. We have a loop of wire instead of just a single wire. We put it in a loop and we rotate it. And it produces current that goes back and forth. For those in pre-cal, produces a cosine or sine wave. There's a lot of math associated with that we're not going to look at. You're welcome. Okay? Good with that? Okay, so here we have a galvanometer. Measures small amounts of current as it goes back and forth, different directions. Good with that? Okay, so what could we do to increase the amount of current created? I mean, because that's what we want to do. Like, step this up. Like, let's sell some more. How could I produce more current? Give me one reason. There's lots of ways. 3, actually.
Spin it fast.
Spin it faster. Spin these loops wire. You spin it faster. Okay? What else could we do? More loops. Put more wire in there. And the third way, greater magnetic field. Good at that? Okay? All right. Another demonstration. Okay. What I have here. Very ornery. Hand crank generator. Okay. So, why is the light flickering? I'm producing what? Actually, before we do this, that's an interesting metal cage. I wonder what these are. What is this? Horseshoe magnets. What am I, when I'm doing this, what am I spinning in here? In here, what am I spinning? Loops of wire. Okay. And producing what kind of current? Alternating. Why is this flickering? Because the current's going back and forth. At some point it hits 0. As it switches directions. You okay with that? Okay. Now, if you spin it fast enough, 60 times a second, this doesn't have a chance to cool down. So it looks like it's continually on. Okay with that? That's old school light bulbs. Those are incandescent. It works like your toaster oven. Okay. Nowadays we have LEDs. Okay. So here, I don't know if you've ever noticed this, but these things flash on and off 60 times a second. If you move it fast, can you guys see it kind of out as strobes? Okay. Yes, no. Okay. Turning off and on because an LED current's only allowed to pass one way through an LED. So when it goes one way, it turns it on, but when it comes back the other, it turns it off. And it's turning these on and off 60 times a second. LEDs don't need to heat up, cool down. So they can turn off, they can strobe 60 times a second. We don't necessarily see that effect until we like move our head fast or like You ever seen that outside of this? Like, next time you're like, well, if you ever see a light strobe, you're like, oh, LED. Hooked up to alternating current. Okay? All right. I want you to experience alternating current firsthand. Okay? So what we're going to do is you're going to take your fingers on either side of the light bulb and you're going to crank. Okay? This, whoa, feels weird. Okay? Doesn't hurt. It's like, whoa, whoa, weird. Okay, that's level 1. I'd like everybody to try that. Level 2, taking the light bulb out, that's a substantial increase. That's not, that's kind of getting on, oh, that's sending pain sensors. Level 3, we'll get our fingers wet, put it on either side. That, I'll just say is painful, but cool painful, you know, in a weird way. Okay, so light bulb screwed in, you're cranking it, go how fast you want to go. Come on up. Once you experience this is good, go quick. We've got 10 minutes. Let's run through this. You go, I would start slow and work up. Okay, good. No, you don't just go straight to the water. Don't go straight to the water.
Wait, where? Ow! Wait, no! Haley! No, go, you go.
It just crank it slow. Touch the metal. Touch the metal. The screws.
I've like learned how to study for this. Yes. Yeah.
Touch the metal.
Are you gonna say
The socket.
like that?
Yeah, touch the metal.
I thought it would be
Where do I put my fingers?
and it's like it's not like you already know how
Yeah, it's.
yeah, I mean you can definitely be mean. Oh yeah, I've got it. Someone else but their calculator broke in the middle. I don't even know.
Oh wait, that was
I was gonna say because I was in there taking a test that day. Yeah, and he was like,
It's so like weird.
yeah, he'll be mean, but then he'll come back up to you.
I think I'm going level 2.
It's like getting shocked. Like, I know.
Okay, everybody, 1 or 2, going once, going twice. Level 2. It is a substantial.
How bad is it?
Just crank it slow.
How bad is it?
That's not that bad.
That's not that bad.
It's like your whole finger.
Oh, so.
Is the goal to turn the light on?
No, the light bulb's out.
It's not that. It's just like, it's just your whole thing. It's the only.
Are they shocking themselves?
This isn't as boring. You just hold the metal? Are you putting the light bulb in?
Yes, I'm putting it on.
I can't shock myself?
You can.
Oh.
Ah!
You're welcome. All right. Keep coming. Level 2.
It's really not that
What's
bad.
level?
Oh, is the shock increase?
Yeah.
Oh.
You're welcome.
What is the purpose of this?
That is definitely stronger.
Let's just experience it in a safe.
It's not that bad.
Oh my gosh.
Let me do that one.
It's just like your
Yeah. Mine's just a little here.
now it's
Everybody else, level 2. Level 2. Go, there's a level 3. Have you done level 1?
No.
Right.
I was distracted.
Yeah, evidently.
Wait, give me level 2.
We're going.
Why'd you go back?
Level, okay.
actually done level 2.
Once we do level 3, we can't go back to 2. Anybody else? No.
Dude, four's like an actual taser.
Okay.
Tasers hurt so bad.
What you gonna do? You gonna get your fingers wet?
Where are the tasers that stop?
You're gonna do it on the other side. Woo!
Yeah, Isaac.
just like
Yep, doesn't take much.
This is the balls we've all dated for a long time.
it's still the same. It really isn't that bad, I promise.
You like?
It's like a little more intense, but it's a little more intense. I was expecting like my whole.
Yeah,
I thought it'd be
much.
much longer, but it's the same.
Same, but a
It's
little bit
the
more.
same finger.
Just like max intensity.
I dumped water on the way, so there's only- I feel like it's still. How can we make it work? Hook it up to the voltage.
Yeah, just spin it faster.
Yo, you need to get somebody cranky this. That's what I'm saying.
Isaac, get your
It's not that bad.
Somebody.
I got it.
Yeah, that's all you
Let
need.
it build up a little bit.
Right here.
Yep.
Let Vaughn just crank it.
Yeah, let Vaughn
No, you're cranking it for yourself.
That's definitely stronger.
Can I crank it?
Yeah, can we have somebody crank it as fast as they can?
No, you crank
That's
it.
level 4. That's level 4. It's helping someone.
Yeah, we just taught you a new level. Level 5.
Anybody else? Going once?
What if I like spin it around and then put my finger?
Yeah, sure.
I can do that?
Yeah. Your left hand.
You gotta wind it up.
Does that actually make it work?
Because it's spinning.
Still feel the second.
Right hand, left hand.
So we're out
You
there.
love it.
If you get out of it, spin it.
Well, yeah, you gotta keep it down.
No, it's just as bad as the second one, but worse.
Is anybody yet to spin it as quick as they can and touch it?
I mean, yeah, there's always one or two every year.
But it has.
Okay.
Do I touch right here?
I'm touching both.
I have to do both?
Complete
I wouldn't want to
circuit.
touch the water. Ah!
Thank you. Adam, got that on recording.
No,
All right.
sorry. I didn't expect it to hurt that.
There's always one or two. All right. So, in real life, in power companies, in generator, like, what do they have spin the wheels? They have big hamster wheel with like thousands of hamsters, like spinning How do they make it spin? You gotta spin the loops of wire somehow. Come on. There's lots of reasons. There's lots of ways to make it spin. How do we create electricity? Generators. How do we spin the loops? Yes. How do you spin them? How do you make it spin? Nope. Good guess. Oh, kids. It's all around you. Okay, look up north in Brookston area. What are those peppered through the cornfields? Windmills. Hey, good job. So the windmills are spinning, and in the housing behind them have coils of wire and magnets. Okay? How else? Water, hydroelectric. We build dams to make the water deep, have a lot of pressure, shoots water through turbines, which are like propellers for water, spin the loops. Okay, how else? Most of the power that's produced in this country is by burning stuff. Coal, natural gas. We boil water, and we shoot it through turbines. Spin the loops of wire. Okay? If we try to do like all like renewable resources, I'm making this up, 85% of 10 to 15% of our nation's power is supplied by natural, like renewable ways. Most of it's by burning natural resources. Okay? The best, in my opinion, the best way forward would be nuclear. That is, that the nuclear reaction boils water, we send it through turbines. It's efficient, it can power enough to like meet the needs that we have. We're pretty power hungry, like electricity hungry, dependent. The problem with nuclear is if something goes bad, it goes really bad. Okay, so you don't want to like camp out around there. Property value plummet. They build a nuclear reactor around your neighborhood. But that's like right now the technology that I could see that we have going forward. Making a bunch of windmills is not going to cut it. Like it's a nice idea, but it's a fraction, small fraction of what we demand electrically. So unless we come up with another way to like get power, like not electricity, but yeah. So that's kind of where we're at. There you go. Yeah, your circuit.